this afternoon I'm representing the yellow community, which also consists of Casey Dillon, Chris Cole, and Stella Tao. And this afternoon I'll be discussing the pressure control system and regarding steady state and step response performance. First I'll go over a little brief outline. I'll begin with some background involving the system, what our system's purpose is, some steady state analysis, which will include the SSOC, some step response theory then building upon our FOPDT model, parameter analysis, then I'll offer some results and close with our conclusions. First, some background. I'd like to introduce our pressure system. The purpose of the system is to supply pressurized air to the spray paint booth, which is actually a simulated model of an actual engine assembly plant in Dunlap, Tennessee. The purpose behind it is to supply or pressurize the booths and then release the contaminated air through filters as regulated by the EPA. The system component we're interested in here is the variable speed motor, the blower motor. It's feedback controlled from the boost, which results in pressure. To expand upon that, our input, our manipulated variable is the power percentage that is given by the motor, and our output controlled variable is going to be the booth pressure. First thing we did in analyzing our system's performance was analyze steady state performance. To do this, we ran our system at several experiments, at several input values to gather the steady state information. Here is a sample, one of our sample measurement experiments, which was ran at 60% input. And it's worthy noting here that we didn't take our average at acceptable range. We needed to start taking the average after about 3 seconds, which was really consistent for all systems. And outlined in orange there is the acceptable average range. And for this particular graph at 60% input, it came out to be an average steady state output at 25.9 plus or minus 3.2%, and that 3.2 is to account for uncertainty, which was the standard deviation times 2. After performing several of these experiments at different input ranges, input values, we were able to put this together to form our steady state operating curve. And this resulted in running experiments from 30 to 100%. And as you can see, our range here, the optimum range was 30 to 9% input, which corresponded to a 5 to 45 centimeters H2O output compression. To further analyze our system's performance, we needed a dynamic time response model. And this involved running additional experiments, subjecting our system to a step function, and then measuring the resulting output. How we did this was we chose 3 ranges. We selected the most linear portion of our SSOC, which was 50, 60, and 70% input, which offered 3 different ranges where we can measure the output, and we took the step up and step down at those ranges. Before going to those experiment results, some theory and background behind the step response. First of all, this is rooted in the transfer function. This function is a model of the first order plus dead time, and it offers a model of the output function. It is built by 3 parameters. First, gain is K, which is the change in the output function over the change in input function, or for our purposes, it's the change in the pressure resulting from the input from the power. Next is the time constant, which is basically a time representation of how it responds, or the speed of reaction. And then, of course, dead time, which is particularly interesting for our system, which I'll explain later. Dead time is essentially the time it takes for a system to respond at the instant the step is introduced. Here's a sample parameter of our analysis for the gain parameter. This is a particular one is for 60% input baseline, which is a step up. This resulted in a 1.05 centimeters H2O per percent. Next one, sample dead time, and this is one I said was quite interesting. Within the capacity of Excel and zoom as much as I could. It's really hard to find a particular dead time measurement for this system. And we resulted in deeming this negligible. To further emphasize this, it zoomed up. It's honestly the stubbornness that Excel is in the little shape function and trying to make it a straight line. It's as you can see, just we had to result in deeming that negligible, unless we had some kind of high-tech device to measure that or further application. But for our purposes, we deemed the dead time for all runs negligible. Not to say that there is no dead time, which that'd probably be impossible, but for our purposes, again, we deemed it negligible. Next, the time constant variable. Again, at 60% baseline input. This one time constant is time it takes for the system to respond to 63.2% of the total change in the step. And this one for the time constant at 60% resulted to be 0.4 seconds. And again, this zoomed in is a little bit easier to read than the time dead time. Time constant resulted in 0.4 again. Here are our results for the gain, how it behaves over each range, lower, middle, and upper. For the up steps, excluding the upper range, they seem to have the same value, and also for the down step, they seem to have the same value, except again for the upper range, which kind of maybe is a parameter result or something. Hopefully we'll find out about that later. Lastly, the results for our time order constant. First, for our time constant. These show again the same results. All step ups seem to be closer in the same region. Also, step downs result in a longer time constant, which will lead us on to make conclusions about behavior of our ranges. Conclusions. The optimum steady-state operating rating range for the SSOC was its input value of 30 to 90%, which corresponded to 5 to 50 centimeters H2O pressure for output. The dead time for the system, again, was negligible from the capacity measurements of Excel. Down steps result in longer time constants than all step-up regions. That's interesting for the time speed response. The system up steps result in a larger gain value across all regions. Lastly, again, looking back at the bar graphs, our conclusions were the time constant and gain parameters have essentially the same value for up steps again in all regions. Down steps also have the same value in all regions. But however, in each region, the parameter values for all step ups and step downs differ a considerable amount. Are there any questions?